Okay, great to be with you today. I'm sorry the couple minutes to get the usual wiring up of the PowerPoint and everything else. My name's David Tennenhouse, and I have the pleasure of being heading up both research and work on emerging technologies at VMware, which includes our recently announced blockchain business. Today I'm going to try to minimize the ad for the blockchain business and actually really talk about this sort of ongoing tension between permissioned and permissionless, or public and private blockchains, and really discuss the opportunities for these to work together, and really my optimism about how they are actually starting to come together pretty nicely. Now, whenever I start this, pretty much the first thing is, hi, I'm from VMware, we're here to help you with blockchain, and the response is, VMware, aren't you the hypervisor company? Aren't you the guys that do virtual machines and virtualized compute? And the answer is yes, and we don't just virtualize compute, we virtualize storage, we virtualize networking as well, and pretty much everything people need to run their private clouds. But we've expanded that over the years. It's actually a much larger company than most people realize. So for example, you can run our stack in public clouds, we provide a service of VMware Cloud on AWS. You can run our stack in IBM SoftLayer. In fact, you can run it on literally thousands of the smaller public clouds that are out there. So we have very much an any cloud strategy. We also do a great deal of work for the telcos and for folks in edge networks. And then working higher up the stack, we help people with application orchestration tools, and application monitoring tools, making sure they're performant, making sure the deployment of these applications and the orchestration of the applications run smoothly in the data center. And then starting about 4 years ago, extended that to any device. So through our AirWatch subsidiary, we've been securing and managing these kinds of devices for quite a while for enterprises. And over the past few years, have extended that to IoT. And the common thread in all this is we're helping enterprises secure and manage their compute, their data, and their networking. So that's just pretty much all the ad I'll do about VMware. I'll just touch a little bit later on the blockchain business itself. But I will say that one of our core values is sustainability, so I like to put in a plug for sustainability. And it's really one of our key contributions. If you think about it, by virtualizing compute, allowing people to consolidate their servers and only use maybe 1/10 of the servers that they would have otherwise, we've helped people save an immense amount of carbon output. So when people talk about all the energy being used in data centers today, imagine how much more it would be if they didn't have virtualization to consolidate the servers in the data center. So to today's talk, I want to basically just divide this into two pieces. One is talk a little bit about what enterprises need. So we're very much an enterprise-focused company. We're not about what consumers need. Often our customers are serving consumers, so we care about them, but I'm just being very clear that's the lens that we see things through, is how can we help enterprises? So when we look at blockchain, and we started on this about 4 years ago, we looked at the cryptocurrency work, said, wow, that's really, really cool, but what can enterprises do with this technology? And then we looked at distributed ledgers, got very excited about that, and carried on from there. So I'm going to talk a bit about that, and then talk about interoperability, the question of how could we put the public and private blockchains together. Pretty much, especially when I get to the later parts of the talk that are more technical, this is all thanks to a team of folks that started as our research team in the blockchain space, as I said, 3 to 4 years ago. In the previous panel, somebody said something about, well, I'd really like to get the cryptocurrency people together with the computer science researchers that really understand this stuff in a deep algorithmic way. And I've just been very fortunate on my team to have some of those folks, people that have been working on Byzantine fault tolerance for about 20 years. And one of them, when she gives her version of the talk, she has the slide that says, hooray, I'm finally relevant. Because after 20 years now, all this stuff is just coming in to be front and center. So I've been fortunate to have a talented team to get this started and now help us launch our business. So from the enterprise perspective, this is not about, for most enterprises, it's really not about cryptocurrencies. It may be about tokenizing assets. There are cases where they care a lot about tokens and the ability to tokenize. Sometimes not fungible tokens, like Ether, et cetera, but non-fungible tokens, tokens that might be bound to, say, a particular financial instrument, a particular instance of that instrument, or a particular asset in a supply chain. And for them, the value then is not coming from cryptocurrencies, it's coming from the underlying distributed ledger, and it's all about centralized trust. And I think for, kind of for this crowd at this conference, you probably know most of the bullets here. I'm just going to sort of remind you that the key challenge is that today with centralized trust, they really have to rely on a third party. Anytime people are doing something together, they have to rely on a third party. And that has two problems. One is, even if the third party is highly trusted, they're still subject to insider attacks, right? So, you can't guarantee that the third party, whether it's a government, whether it's a regulator, whether it's an industry self-regulator, you can't guarantee that they haven't been compromised. So there's a problem right there. And then the other problem is that the third party adds friction, and it's not just adding, they add a friction because they usually add a fee, right? So we'd like to get those, fees back and not have to pay fees to the third party. But it's not actually just that fee, it's a friction to starting new consortia, right? Every time you want to start up a new supply chain or a new financial clearinghouse, you end up actually having to institute a whole new trusted third party. So you actually have to put an entity into place, you have to hire people, you have to establish new standards, new processes, et cetera. So we see distributed ledgers as giving us this sort of way to have a reusable platform that could be used across many, many different consortia and speed that process of consortia formation. Now, having said that, we then get to the question which I'm about to address about, well, what about, private blockchains versus public blockchains? And in one of the sessions earlier today, I heard another speaker saying, gee, they're seeing pretty much all of their customers going to private blockchains because if you've got an existing consortium, you've got an existing operation, it's sort of a straightforward path to adoption. But I'm not going to try to argue today that that enterprises must use private blockchains. I think Vitalik, and I've got some quotes here, had it approximately right. He limited this to financial institutions, but even non-financial institutions that are involved, say, in regulated supply chains, so anybody in the food industry and the pharmaceutical industry, many flavors of electronics, avionics parts, there are many, many different parts of the economy where you do have a requirement to limit the participants. So could you do that on a public blockchain? Well, the answer is yes, by having a whole bunch of permissions and extra authentication, et cetera. So it's not that it's impossible, it's just, as he says in this rebuttal quote, it kind of becomes a Rube Goldbergian kind of thing, right? You're sort of going to a lot of extra work in order to use the public blockchain, and it might be simpler and easier for you to stand up a private one. And so, I just wanted to clarify that the arguments I'm making aren't about what's possible, it's more about, what looks like the easiest, most direct path for our enterprise customers today. Now, in the future, it might be different, right? In the future, you might have a really widely used public blockchain that is really robust and reliable and where everybody trusts the validators, et cetera, and where it becomes a no-brainer to just sit on top of it. But that's not where we are today, and probably not for the next 5 to 10 years. The one quibble I'd have is Vitalik said that it's an argument only about efficiency and not possibility. So I agree it's not about possibility, but I think it is about more than just efficiency, right? Sometimes it is about regulation, it is about democracy, government processes, et cetera. So, this chart is meant to sort of compare and contrast. And again, I think for this audience, I don't have to go through this bullet by bullet between, kind of the public blockchains and the cryptocurrencies and what you need to mount an enterprise strength application. And I think the key and most important item on here is the known counterparties. Interestingly, the cryptocurrency environment, people were actually striving for anonymity. In business, you really do need to know who your counterparties are. You need to assess counterparty risk, right? If I'm doing a transaction, if I'm buying an option from you, I need to know whether or not I think I can trust you to deliver on that option, right? Can you actually deliver the goods, and let's say it's an option or a future. Will you deliver the goods at that agreed point in the future when I'm supposed to get them? Similarly, if I'm in a supply chain arrangement with you, I need to know who I'm getting this from and who I'm dealing with. So both at the validator level and at what you might think of as the client level, you really want to know things about the counterparties. So we think that's kind of one key aspect. There's a bunch of other items, but some of these do come down to performance, and that the traditional or the early, Bitcoin-style public blockchains, not very good on throughput, very high latency or time to finality, and terrible on energy. Now, all three of those are actually improving. Interestingly, they're improving by kind of stepwise moving towards Byzantine fault-tolerant consensus protocols. And I'm going to talk about that quite a bit in the next few minutes. But if we look on the enterprise side, you care about that. You need high throughput, you need low latency, and you actually want to be able to do this across a fairly large but tractable number of nodes. And if you're VMware and you care about sustainability, then it's got to be energy efficient. Now, I just want to underscore the comment I made about the validators. You need to know your counterparties. You also need to know something about the validators to know, kind of how safe this system really is. And in the early days of Bitcoin, we all had high hopes about this, that, you've got these economic incentives and miners won't collude and it'll be really hard for people to take control. But I think people have now realized that these highly decentralized systems actually aren't, right? And this is a chart from Are We Decentralized Yet? And if you're not aware of this, I think most of the people in this room probably are, but if you're not, you should go take a look at that site and be very cognizant that most of these public blockchains are actually, in a sense, controlled by a fairly small number of players. So, again, from the enterprise point of view, there was already a good answer out in the computer science world to be able to get reasonable throughput and latency, although it wasn't really scalable to a large number of nodes. So this was Byzantine fault tolerant. And to be honest, the reason it didn't do better is it had been developed 20 years ago and people didn't really have an immediate application for it. So they got to a point where they said, well, kind of good enough to do the, publish the paper. And they didn't continue developing the thread of, okay, now how do I scale that from, say, 4 or 8 nodes to hundreds of nodes? How do I improve the throughput? How do I reduce the latency? But BFT consensus, or Byzantine fault-tolerant consensus, has sort of some nice properties, or can have, and these are the key properties we focus on. So first and foremost, you want it to be safe. In other words, you want to know that it does correct things and functions correctly. That turns out to not be completely easy, but doable. And by not completely easy, I mean that, like in cryptography, usually the crypto algorithms are good. The implementation and the engineering is where security falls down. And so you have to look out for safety. Linearity is really a proxy for saying, I want if it's linear in the number of messages I have to exchange, then probably the throughput will be good. If it's quartic in the number of messages that have to be exchanged, let alone cubic or quadratic, then it'll probably be bad. And responsiveness really has to do with time to finality. So we've worked a lot at improving that old BFT. The best implementation in the past was something called PBFT. And last summer, we released Project Concord. It's an open source project using something that we now call Scalable BFT, SPFT. And that's the basis for our blockchain business, which we announced a few months ago. And I'm not going to do an ad for that business, but if you want to learn more about it, please contact me afterwards. So SPFT, as I said, has some really nice scalability properties. These are some comparisons between SPFT and the older PBFT. And what I want to say is if you went and ran the old PBFT code, believe me, you wouldn't get these numbers. So this is after our folks kind of took a bunch of their best ideas, improved PBFT as much as they could, and then added the new features that we use to make things scalable. And on the left you can see the throughput's better, and on the right the latency is lower. So this is what you want. The other important thing I'll say about this chart is this is done with 200 nodes. So if somebody shows you performance charts, the two questions you should ask is, there's actually three questions. How many nodes? How spread out were the nodes? If they're all in the same data center, then it's easy. And also, how many failures? Because the whole idea of this Byzantine fault tolerance stuff is for it to work well when people are attacking it and when it's failing. So this particular case is for 8 failures, but we run this up to 64 failures for 200 nodes. That's getting you to your 1/3, which is what you expect a BFT system to tolerate. So those are the kinds of questions you should ask, and they're the way we try to do our performance comparison. And if you're wondering how do we get the improvement between SPFT and the juiced up PBFT, one of the key mechanisms is that what we call, essentially we move to a linear communication and an order of magnitude reduction in the communication cost. And we do this by saying instead of everybody having to sort of pass their votes or certificates to each other amongst the validators, we can have a mechanism where if I've seen something from 2 of you or 3 of you or 4 of you, I can actually combine your signed signatures into a single message. So everybody doesn't actually have to send messages to everybody in order to make this thing work. And this uses a technique called threshold encryption and allows you to sort of get a significant reduction in the common case in the communication cost. Interestingly, that same trick, and this is what's shown in the box on the right, also means that the client or customer can actually just get one message back that carries the proofs from a whole pile of other players instead of having to collect up a whole bunch of messages. So lots of improvement. I'm going to skip over this one, carry on. Here we've got a question now about public or private, and my argument is actually they go better together. As much as I'm a big champion of private or permission blockchains, I see a lot of advantages to public applications as well. So for example, if you've got fungible currency-like tokenized assets, very fungible, you want lots of people to be able to trade and use them, a public blockchain seems like a good solution. But also something I'm very excited about are public records. Things like property records, tax records, places where you just want to make authoritative data, places to be able to publish, if I want to find out what's the latest authoritative version of software of a particular, say, driver for some piece of consumer equipment that's out there, this can be a good way to do it. So we'd like to figure out then, can we get these two things to work together effectively? Could we achieve interoperability? And it's something that I think is actually quite feasible and at various layers. Some of the key things that you need to figure out here is, yeah, but these different systems really have different criteria for the validators and who's a validator, and how are we going to respect those differences? And I just want to sort of put a throwaway comment for the moment that there's actually a lot of historical examples of validators that are not based on, proof of work is based on basically who's the wealthiest, who has the most computational resource, who can spend the most money, right? Proof of stake is kind of who's acquired the most of something. It could be a specialized kind of token, so it could be a certain flavor of money. But there have been lots of other techniques, including things like the DNS, where the validators are basically a really dedicated group of people that you've never heard about, sort of individuals. They work together in various organizations, and they just make things happen so that the DNS works for us. So there's lots of ways to pull this off. Actually, another great example is cryptography, where, to be honest, the validators are the mathematicians of the world. You may not think of it this way, but essentially, you don't really know that those crypto algorithms are as secure as you think, right? Most of us don't have the math skills to know that. What we trust is that the world's top mathematicians haven't come forward, and none of the world's top mathematicians have come forward and said, I've broken that algorithm, right? And so we're that's our validator set for much of crypto. So there's some interesting alternatives out there. The other interesting thing here is that although proof of work and proof of stake and kind of other proof techniques look a lot different, really they come down generally to trying to get some threshold. You're essentially getting some voting amongst this group of validators, and you need to get some threshold fraction of them to have agreed to something. And the validators basically are based on some resource. Either it's computational power or currency, as I said, or it's reputation, right? Or that they're members of a group. They're elected officials. They're regulators. But these are not as dissimilar as they look when you back away from how do you get to be a validator to what do validators do? Well, they try to get to some threshold agreement as to what's gone on. So the other point I want to make here, just before diving in to some of the technical part of pulling these things together, is that interoperability is also a path to standardization. In other words, interestingly enough, if we can get these disjoint things to be interoperable, what you might think is we're promoting heterogeneity. We're going to allow things to be different for a very long time into the future. But something we've learned in the software world is after you get things to be interoperable, you drive competition amongst them, and very quickly we consolidate on just having a couple, right? So ironically, if we promote interoperability and heterogeneity, we will actually drive things towards standardization faster than you might think otherwise. And a key step towards that in other industries has been getting a common architectural model. And the blockchain world's already, well on its way. I think pretty much people have reached consensus on this model. So then our question becomes, at what layers do we try to get interoperability? And here today, you'll have seen in the academic side and a bit here, lots of work going on already on token exchange. So I'm not going to talk about that. I think people figured out pretty much that they can get tokens exchanged across different types of blockchains. We can probably get smart contracts exchanged across blockchains. That's trickier. The optimistic point I want to get to today is I think, and this is a reach right now, that we can actually even get towards state exchange across disparate blockchains. And the reason here really is that pretty much we're starting to get consensus on what consensus is about. In other words, where pretty much all roads are leading to Byzantine fault tolerant of some sort, because BFT is being used to sort of juice up proof of work and proof of stake, right? And being used to speed them up, both in terms of throughput and finality. Now the catch here is, although BFT's got all those great properties I talked about before, traditionally it had some problems. It had at least quadratic communication, right? And in some cases worse. It had limited scalability. Now I told you that we already kind of dealt with that with SPFT, but it's notoriously hard to get right. Now if you don't believe me, you could just see people make a career out of writing papers showing the bugs in other people's BFT algorithms. Not just in the implementation, but actually in the algorithms. This includes some folks from other places, includes some of the folks on my own team. And then in addition to those sorts of problems, the other thing is people often release things and leave the actual implementation of the BFT as an exercise for the future. So when you read the fine print, you find, oh, they haven't actually done it. Well, that's, suggests it's probably hard. And so it's not for the faint of heart, and the question we've been asking ourselves is there a way to make it way simpler? And that would make it easier to get correct implementations, and it would still be performant. So these were the properties I talked about that you want to get, and what I'm here to say today is, yeah, I can't tell you exactly the way, but we really see this glimmer of a path forward coming from some work some of our researchers have done on something called hot stuff. And the diagram here is just the classical, sort of blockchain-style diagram What they've been doing is realizing there's a way to rethink, or recast SPFT using some of the great learnings from the blockchain community. The learning kind of from the BFT community is what you really want to do when you're doing fault tolerance, Byzantine fault tolerance, is pull together what's called a quorum certificate. You need to show that out of a community of what's called 3F plus 1, that you got at least a third, 2/3 plus 1 of the votes to agree to something. If 2/3 plus 1 of the validators agreed, then we're in good shape, right? I won't go into the why the 2/3 plus 1, but so what you do is you kind of collect up proofs, certified, signed certificates from these folks, and when you've got enough of those, you have a quorum certificate. I'm getting the times up here, but I got to go through this. This is really very cool, and it's that with a very simple set of voting rules, we think that we can actually represent pretty much all the algorithms that are out there. So I won't go through the details of the voting rules, but what I'll say to you that is with those voting rules, you can have something that we call just a one chain. That means in one block, I have a certificate for the block that came before me that proves that the block came before me had enough votes. Now, if you stop just there, you'll actually be able to solve the problem to make sure that you resolve forks, which is the hard problem in blockchain. But unfortunately, although you actually had the proof for it, you haven't shared that with everybody, right? So you haven't really fully solved the problem. It turns out that if you do two chains, you can actually solve the exchange. In other words, you sort of hold off agreeing that the first thing is done until you have a chain of two of these certificates. Then you've actually sort of solved the question of which fork won and spread that information so that enough parties actually know about it, but they can't necessarily prove it to somebody who is stuck still thinking one of the old forks was the winner. But if you wait just a tiny bit longer till you can collect up a chain of 3, then you're done. And you can connect these chains together. So I'm sorry I had to go through that so quickly, but this is basically the basis for what we call hot stuff. It turns out you can actually relax the rules slightly. I won't go into that detail. What's interesting about this is this simple set of rules explains basically all these protocols, right? So all of these different protocols can be modeled with that same set of rules. And that's what kind of gives me optimism that we can make this all way simpler and that we can pull it all together. If somebody wants to talk to me later about message complexity, we've got the table on relative message complexity that shows this gets you the linearity, it gets you the responsiveness, and we think it's going to actually give us a great path towards interoperability. So I just want to close with this last quote from Vitalik, which is, that two different ecosystems may evolve, public and private, to serve the different constituencies, but they can actually do much better if they work together. So thank you very much, and hope you enjoy the rest of the day.